Good afternoon. My name is V. Pradip Reddy and I am from Aeronautical A section. My aerospace propulsion topic is paragliders, launch trajectories universal. Introduction. Paragliding is a young adventure sport consisting in flying lightweight, free flying, foot launched glider aircrafts with no rigid primary structure. For a physicist, it truly is a bottomless drawer of fascinating unexplored phenomena, combining a variety of fields covering fluid mechanics, fluid structure interactions, flight mechanics, material science, micrometeorology, and even game theory in the context of understanding exploration, optimized paragliding competitions. Since the first prototypes, paraglider wings haven't ceased to evolve both in terms of performance and security. While most of the research done by paragliders manufacturer has focused on optimizing wings for steady flight paces, unsteady regimes have only received limited attention. In particular, many questions remain unsolved when it comes to the dynamics of stalls or wing collapses combined with the aircraft specific pendulum motion. Some diagrams of paragliders. Real scale experiment. Concerned with the difficulty to downscale or characteristics of a real glider, we decided to convert our results to real scale experiments. Using a 13-meter, two flat single surface glider, we were able to record a few launches on a calm day at a PUD home. A seasoned test pilot was asked to launch with low and strong traction strength respectively. Unlike laboratory experiments, a slight wing as was present here with speeds around 7 meters per second measured during each run. Real scale experiments, the time step between shots in 200 ms. Schematics supporting the theoretical model. As such, they are not expected to stand in the fundamentally unsteady conditions of launching phase. For one thing, within steady flight theory, the wing should stall in the very beginning of the launch as the angle of incidence alpha tends to pi by 2, which is obviously not the case here. Measuring unsteady lift and draw coefficients would be very interesting, but doing so comes with its own difficulties and would require an entire and independent analysis way beyond the scope of the present story. Note that such unsteady lift and drag coefficients are expected to be highly interactive, incretive, as in the early stages the wing is not fully inflated and thus its very shape varies over time. N equals to half rho SCL of alpha v square m e perpendicular. D equals to 1 by 2 rho s cd of alpha v square m e parallel. Discussion. The study revealed a number of other exciting questions such as optimal folding of the wing for a comfortable launch in strong wind conditions, or the differences between regular and single skins wings during the unsteady phases, and the launching phase in particular. Single surface gliders are known to launch much stronger than their regular counterparts. This is often attributed to the fact that they are lighter and thus have less inertial effects, but we believe it can also be related to the fact that the inflation phase is much faster as argued in section. For regular double skin gliders, the question of the simultaneity for the chamber's air filling and rising phases is an intricate one. Indeed, one expects that the lift coefficient grows progressively as the chambers fill with the air, which explains why the wing starts to take off before the glider is fully inflated. Thank you.